right then. Guess we can start. So, can everyone like see the screen? That's fine. Or... All right. So the last week was about polygons, and this week is going to be about solids. So we're kind of doing what I think is just geometry for the first few weeks. The solids are basically 3D geometry, and honestly, the techniques that you use for solid geometry problems is really just simplifying the problem into a two-dimensional problem in most cases. So to do that, you have to like understand just like the most common shapes that you would see involved in these kinds of problems. And here is another table with cool properties of everything that I found. And yeah, so we can just go over them. First one is called a cuboid, or more commonly a rectangular prism. It has three defining like values, which are its length, its width, and its height. And the volume of this shape is just the product of all three. And but I should mention each of these top parts where we have the categories like name of the solid, figure, etc. So basically, we have the lateral surface area is going to be like the area of all the faces of that solid, not including its base. And you're really only going to see this for shapes such as pyramids, cones, and cylinders. Not too much with prisms because they're very symmetric for the most part. And then next is total surface area. This is simply just adding all the areas of every single face. Not much more than that. Volume is just like three-dimensional area, or you can think of it as all the points just inside of the figure. And this last one called nomenclature, that literally just means what the variables in the figure represent for that shape. All right, so there are like a lot of formulas here in this table, and a lot of them are, or all of them are very useful, and they're very similar to each other, so they're kind of easy to remember. So I think the more important ones are going to be to know the cuboid, because in general, this is like a 3D rectangle, so you're multiplying length times width times height to find the volume, and this would be like the same for a cube as well, because a cube is just a cuboid, except for every face is a square. Right. So then next, I'm not going to talk about the lateral surface areas for these two, because that's really just adding the rectangles on the faces, which is not very complicated. So next would be a right prism, which is a prism with any kind of base. So the base can be any shape, a triangle, square, pentagon, hexagon, etc. And its faces, or its lateral faces, are all going to be these rectangles, and it has two bases of the same shape. And so you can think of it as like a shape, and then you kind of elevate, you kind of just keep on stacking the same shape on top of it until you get a solid. So the way you would find the volume of this would be to take the base of your shape and then multiply by the height of the prism. So kind of like how cuboid is length times width times height, and the area of one of the bases just like length times width. So in essence, it's still going to be like base times height as the volume of the figure. All right. So I'm pretty sure that that volume formula is pretty intuitive, because like you're kind of like taking the like a height number of these bases next to each other. So that would be kind of why the volume is what it is. The lateral surface area of these prisms, where not every face is like a rectangle or square, is going to be just the perimeter of the base times the height. And this is because you're adding all of the rectangles on the side, and there are an equal number of rectangles like on the lateral surface area as there are faces in the base, because each like pair of faces from these two bases corresponds to exactly one rectangle. So that would like be the explanation for the lateral surface area, and that's kind of it for right prisms. For the right circular cylinder, or just cylinders in general, because whenever you see cylinder in a problem, this is what it refers to. It's just like two circles as bases and one curved height, or one curved like rectangle as the height, where like the entire way around is the rectangle. So for this one, your volume is going to be calculated as you would expect for the shape, where you take the area of the circle, then multiply by the height. So pi r squared times h. And its lateral surface area is going to be the circumference of the circle on its base times the height. And the reason why this works is because you can unfold the cylinder. So like the cylinder normally looks like this, you can change it into like a rectangle. And where like this end and this end, so two ends on the right and left, are supposed to be connected to each other, where one of these lengths, this is 2 pi r, or the circumference of this circle, and this is just the height. So that would be why the lateral surface area of a cylinder is 2 pi r times h. And simply because you can kind of make a vertical cut on the side of a cylinder and just unfold it into just a rectangle. All right. And by the way, if anyone does have any questions regarding anything I have said so far or will say, feel free to ask. And this goes for anything in this class. So yeah. Next is the pyramids. And the pyramids are kind of like prisms, except for there's only one base. So a pyramid has a base of any shape, can be square, triangle, etc. And it has this one point called the vertex. And well, the vertex is going to be just like the one point above the base that has an edge connecting it to every other vertex in the solid. So like for a square pyramid, as shown, you have, it looks like one of the pyramids of Giza in Egypt. It's like a pyramid. Another one would be a tetrahedron, where you have a triangular base and this one vertex here. And the cool thing about tetrahedrons is that every single vertex can kind of be seen as this vertex up top, because just because of how many vertices the tetrahedron has. We'll talk about that later. I think that is like the construction of a pyramid, and the volume of a pyramid, which is not so obvious to calculate, but it's very important to know, is 1/3 base times height. And I can't give you a really good reason right now for why this is the exact area formula, but intuitively you can think of it as a pyramid is kind of like a three-dimensional triangle, and the triangle's area is 1/2 of base times height. When you compare it to like a rectangle with the same base and same height, it's half that area. And since like we're in 3 dimensions here, and you can think of a pyramid as just like almost a triangular version of a prism, you can just change this 2 for 2 dimensions into 3 for 3 dimensions. So you have 1/3 base times height. Again, I can't really give you a formal proof of this, but just know that this is the area formula for a pyramid. And this is a very general formula since it applies to any pyramid with a base. So basically all pyramids. And for their lateral surface area, this one is not very friendly for, this is not very friendly to find. And this is simply because your like lateral surface area is going to be these kind of arbitrary triangles. And you'd have to find this height from the vertex to the base of the triangle. And that's not very obvious and not very universal when you're working with other pyramid types. So when you're calculating lateral surface area, you really just need to find the slant height. And so basically every time you have a every time you have a pyramid and you need the lateral surface area, you have to use the Pythagorean theorem. So if we take just a regular square pyramid, so the base is a square, you have to like make the three-dimensional altitude, or the one that goes from this vertex to center of the square, and you have to connect that to the midpoint of a side, and then the slant height would go like down the middle of one of the faces and also like connect to the midpoint of one of the sides. And this is the right angle because this is a right pyramid. So then you would use like the Pythagorean theorem to find the slant height. And after you find the slant height, then you can use formula for the area of a triangle to solve for lateral surface area. And in general, for like pyramids, the lateral surface area and like the base surface area, the surface area of the base, or the square in this case, they're not going to be related in like any other way. So when you find the total surface area, you really just have to find them separately and add them. That's really it. And next is a cone. A cone is simply a circular pyramid. So the base is a circle. And so it's kind of like, it is to a pyramid what like a cylinder is to a prism. So like the formulas are essentially still the same for a cone. So its lateral surface area, lateral surface is different. Its volume is still going to be 1/3 of base times height. But lateral surface area is a little bit special. And it's kind of because when you're not given this slant height L, you can find the lateral surface area of a cone by like changing it into a sector of a circle. And this is like one of the main properties of a cone. It's that when you like make a cut on the cone, similar to like you would with a cylinder, when you like unfold it or something like that, you would have this sector of a circle where these two ends are supposed to be connected to form the cone. And the way you would find the angle that this sector is just by comparing the radius of the base of the cone to the like slant height and the height of the cone, respectively. And the idea is that the circumference of this sector with radius slant height is equal to the circumference of the entire circle with the radius be the radius of the base. So then that would give you the ratio of the two radii. Then from there, you could find the area of the sector. So that would be, those would be like the steps to find it if you ever need it. I don't think that this is used too often, but it does come up occasionally. And yeah, to find the total surface area, you just add that to the base. So that's not really special. So then lastly, we want to talk about the sphere. And the sphere is just a three-dimensional circle. It's a set of points in a three-dimensional space that are equidistant from a certain point, which is the center. So these formulas are not very easy to just derive, but the volume is going to be 4/3 pi r cubed. I don't really think there's a great explanation like at this level of why this is true, but it is something you have to remember. So 4/3 pi r cubed. And the surface area is 4 pi r squared. Again, not a great like explanation right now of why that's the case, but these are very, very important to remember. And that's really all I want to cover for spheres. Just these two formulas. You just have to know them. There's really no other way. And lastly, hemispheres are simply just spheres cut in half. So you can find that area is exactly half of the sphere, and its total surface area is going to be the surface area of like half a sphere, so 2 pi r squared, plus this circle with the diameter same as the sphere, which has area pi r squared, which makes it 3 pi r squared. And of course, this lateral surface area is just going to be not including the circle, so it'd be 2 pi r squared. So that'd be it for like what I think are the most basic shapes and the most common shapes. So I think that's really all you would have to remember for everything here. So yeah, if anyone has any questions, feel free to ask. If not, I'm going to move on to tetrahedron. And actually, I'm not going to. Okay, never mind. I am going to talk about it. So sometimes this is kind of like a special shape. You can think of it as some problems that you'll see. They're just referred to as tetrahedron. It means a triangular pyramid with every side is an equilateral triangle. I'm sorry, regular tetrahedron. A regular tetrahedron has all sides as an equilateral triangle, and just 4 sides, 4 vertices, and yeah, as I wrote here, the height from the vertex to the base lands on the centroid. And this is true for basically all pyramids, where when you draw the height from the vertex to the base, it'll land in like the center of your shape. And the center of an equilateral triangle is just the centroid. So yeah, it's not like too important to know because these are all things you can kind of figure out regardless of me telling you, but yeah. So another shape you might see is an octahedron, and this is simply just 2 square pyramids glued together. And it's called an octahedron because it has 8 faces. Usually these octahedrons are going to be, well, not necessarily equilateral, but the two pyramids are going to be congruent, and you would find their volume and surface area by just treating the pyramids separately and adding them. So again, the only thing you really know about octahedrons is how they're constructed. Everything else can be figured out from previous information. And lastly, I want to talk about truncated shapes. And this usually refers to pyramids or cones, and it's simply just when the top is cut off parallel to the base. So it looks kind of like a trapezoid. And you'll see it like something like this. And this is a cone, supposedly. And then just this top cone just disappears. So you would have something that looks like this. And to find the volume of this, you would have to like assume what would the volume be if the top part of the cone was not cut off, and then find the volume of the top part that was cut off and subtract. There isn't a very like great way to find it or consistent way to find a volume of this truncated shape without doing that. All right. So I didn't write this on the notes, but another thing I want to talk about, and the last thing for three-dimensional shapes is going to be called Euler's polyhedron formula or theorem or whatever, something. I don't really know the ending, something, but it just says that for any polyhedron that does not have any holes, which in really anything that you'll see won't occur, you'd have like the number of vertices plus the number of faces is equal to the number of edges plus 2 for any solid. So for all solids, this is true. And yeah, V is vertices, F equals faces, and E equals edges. And again, I can't really show you the proof of this, but this can kind of be, you can check this with any of the shapes in this table right here. So for example, a cube has 6 faces, has 8 vertices, and has 12 edges. So a cube works here. Oh, and I should mention that a polyhedron is kind of like a polygon solid. So it does not include spheres, anything with a curved face, only those with these like straight faces, like a polygon. So yeah, that is the last thing I want to talk about. And time for my tips, I guess. So the first one would be draw a decent diagram. And what that means is just make it look somewhat three-dimensional so that you can kind of see how everything fits together. Usually the hardest part about these types of problems is just visualizing everything. So if you can get like a diagram that helps you visualize it, that is like half the problem done already. All right. Again, the Pythagorean theorem is very useful because a lot of times the figures that you'll see will be right figures, as in they're like something is going to be perpendicular to like their base, and it's going to be pretty obvious when you see it. And just like with normal 2D geometry, you can dissect volumes. So like splitting up into parts that you know, like with a truncated cone or pyramid. And sometimes working backwards, this is more of a general tip. A lot of times just you take what the problem's asking for and then try to see how you can get there, especially when like you don't know like where to start, what to look for in the problem. You try to look for what might be helpful to achieve your end goal. Yeah. But like not last thing, but I bolded this because I thought this was the most important one, and it's to take cross sections. So a cross section is basically like if you can cast your 3D object or figure onto a 2D plane. So you take any plane and you can kind of cut your 3D figure, and then whatever like intersection that plane has with that shape will just be on your 2D grid. So like if you take a sphere and a cross section, like it doesn't really matter how you do it since it's a sphere. So if you take a vertical cross section, it would just be like a circle, and a cross section of a sphere is a circle. So like of a prism would be a square. The cross section would be a square. And for other shapes, such as like a cylinder, if you take it vertically, you'd have a rectangular cross section. Horizontally, it would be a circular cross section. So in general, all it does is it simplifies it into a two-dimensional problem, which is easier to deal with. And lastly, I'm talking about tangency. And basically, in 3 dimensions, tangent shapes works basically exact same as it does in 2 dimensions. So tangent spheres basically intersect at one point. So they're like next to each other. If like if a shape is tangent to a plane, then that means that usually a sphere that is, that means in the radius from the circle, from the center to the tangency point is going to be perpendicular. So that is a property of tangency, and this kind of works because of cross sections. So yeah, just know that cross sections kind of allow this tangency to work in three dimensions. All right, so I think this is a bit of a shorter content part, but so I think we do more problems this time. So yeah, I think we can get started. So this first problem is solid tetrahedron. It's sliced off wooden unit cube by a plane passing through two non-adjacent vertices on one face and one vertex on the opposite face, not adjacent to either of the first two vertices. So the tetrahedron is discarded and the remaining portion of the cube is placed on a table with a cut surface face down. So what is the height? All right, so the first thing you should do with these kinds of problems is to draw a diagram, especially if it's 3 dimensions. So you start off with a unit cube, so you can draw something that looks like a cube. Doesn't really have to be great, but looks like that, right? And then it says this plane passes through two non-adjacent vertices on one face and one vertex on the opposite face, not adjacent to either of the first two vertices. So we can choose any two vertices for the non-adjacent vertices on one face. So I'll just choose these two. And then the third vertex can either be this one or the other one in like the far corner. But since it's symmetric, it doesn't actually matter which one I choose. So I'll just choose this closest one because it's easier to work with. And lastly, since we know it's a plane, that means that the line between each of these 3 points must be on the plane. So like you can see now the intersection of this plane with the cube is going to be that triangle. Okay, and this now says the tetrahedron is discarded and the remaining portion is placed on the table, and you have to find the height. So if you can think about it, it's like you cut like that corner off the cube, then you like turn it over and place it on that part you just cut. So the height of the cube would just be the height of the cube normally if you did not cut like that part off, minus the height of the part that you cut off. So first to notice is that the height normally would just be square root of 3. And this is because this is a unit cube and you're putting the cube kind of on a vertex. So the height of the cube would just be the distance from one vertex to the vertex on the complete opposite side of the cube. And this is called the space diagonal. And the space diagonal of a cube is just square root 3 times the side length. And this is true because of the Pythagorean theorem. So like if you take just this bottom face, the face diagonal, so just connecting 2 points on the same face, is going to be square root of 2 because the sides are 1 and 1. Then like this side on the left is 1. The entire space diagonal, this length of root 2, and this side of length 1 all form a right triangle. So the space diagonal is length of square root of 3 from the Pythagorean theorem. So that's why the total height that you're subtracting from is a square root of 3. So now you just have to find the height of this tetrahedron. Now, how would we do this? So first of all, does anyone have any ideas as to how we should find this height that we have to subtract? I'll give you all like a minute or so to think about it. All right, so does anyone have any ideas? We'll say that there are multiple ways to do this. So,
Wait, could you repeat your question?
the question is, how can we go about finding the height of the tetrahedron that we need to subtract?
I think you can do like one way you can find volume is um like using the right triangle side, like thinking of it, or like taking the right triangle area and then multiplying by base and then finding a third of that. And then another way you can find the volume is by taking the area of the equilateral triangle times the height, which is what we want, and then dividing by 3. So then you can solve for height.
Yeah, you are correct. You can find the volume of this tetrahedron in two different ways. So in a lot of geometry, you can solve it by expressing some value in multiple ways. So the other way you could have done this was finding the length from the centroid of this equilateral base to one of the vertices, which is the circumradius of the triangle, and then using a Pythagorean theorem with the side. But I like the volume way better because it's a little bit easier to work with, I think. So the volume of this tetrahedron is going to be first with the right triangle way. We know that this edge, or all three edges, are going to be perpendicular to each other because this is a cube and everything is perpendicular in a cube. So this means that one of the edges is going to be the height of this pyramid, and the two other edges are going to form the right triangular base. So then the area of this, if we let, well, the sides are 1. So the height is like 1 and times the base. The base area is just going to be 1 times 1 over 2. So it's 1/2. And then we divide by 3 because the area of a tetrahedron, or in this case, a right pyramid, is going to be 1/3 base times height. So then that's just 1/6. So now we can find the volume using the equilateral triangle as the base. And we know that the equilateral triangle has sides of length √2 because those are the diagonals of each of the faces, which have sides of length 1. So from the area formula for an equilateral triangle, or if you don't know it, you can derive it just by drawing an altitude and using the Pythagorean theorem. It's just going to be s squared times the square root of 3 over 4. And here s is equal to 2. So this is just square root of 2 squared, or 2 root 3 over 4, which is just the square root of 3 over 2. So that is the area of the base. And now you would have to find volume using this and the height. So the volume is equal to 1/6. And we also know the volume is also equal to the square root of 3 over 2 times this height we don't know times 1/3. So this means that volume is equal to the square root of 3 over 6 times the height, and the volume is 1/6. So then this just means that the height is 1 over the square root of 3, or root 3 over 3. All right, and from here, you simply just subtract minus square root of 3 over 3. We get the height as 2 root 3 over 3. And that's the answer to the question. So yeah, so mainly for this problem, I guess the big idea is just first off to visualize what is happening. And after you visualize it, just you can use the properties of how to find volume, I guess, to figure out the height. So this is rather simple, but I think it's a good introduction into how you should I guess, view these solid problems. All right. So next we have this one. It's a solid cube of solid length 1 is removed from each corner of a solid cube of solid length 3. How many edges does the remaining solid have? So again, you'll notice that the number values you'll see in this question are not very useful because you only ask how many edges. So if we first have like a cube, then it would kind of be like if we take a unit cube off of each of these corners. I'm not gonna draw for every corner, but it's kind of like that. Okay. Well, now we have a few options. First, and none of these options are necessarily wrong. You can try to just count how does the number of edges change as you add or as you take away a cube from each vertex. Then you can multiply for all 8 vertices. And this is probably the way I would do this. And the other way is to use Euler's polyhedron thing that I said. I want to say it should be formula. I'll just call it formula. Euler's polyhedron formula. You can use this as well, since this relates all the vertices, faces, and edges. And this is, even after taking away all the unit cubes, this is still going to be a polyhedron. So I think I'll do this both ways. So the first way, when you take a unit cube away from a corner, you aren't changing any of the existing edges. So what I'm saying is how there's still this like sliver of an edge of this like former edge that's still there actually. This edge never gets like changed, so it's still going to be there, and same for every other like edge of the cube. So you know they're going to be the 12 original edges still there. All right, and now when you add or when you take away the unit cube, you add 9 more edges. So you have on this face 1, 2. So it's like if we look at just one face, for one unit cube, you'd have like 1, 2 extra edges here. And this would apply for all 3 faces that this unit cube kind of takes away from. So this would be like 3 times 2 equals to 6 on each of the faces. And then now you can think of, this is kind of hard to imagine, but like you think like inside of the cube. So the edge that was it's in a location that was once inside the cube, but it's not anymore. There's gonna be 3 there. So what I'm talking about is it's much easier to visualize for this top unit cube. So if we take away if we take away if we take away this cube from this corner, then there's still going to be, then I erase it, it'll look something like, there's still going to be like these 3 vertices on 3 edges on the inside of this cube. So in total, you'd have like 1, 2, 3, 4, 5, 6 on the outside, and 7, 8, 9 on the inside. So each vertex adds 8, and there are 8 vertices. Each vertex adds 9, and there are 8 vertices. So you'd have 12 plus 8 times 9, or 84 edges in the remaining solid. So it is kind of easy to lose track of some edges when you do this problem. So yeah, I guess the best thing I'd say is just you have to be really careful when you're drawing a diagram and trying to visualize it in your head. So I do want to go back to the Euler's formula version, which is using the total number of edges and vertices. Oh, that's not right. Like this, we can just count the number of faces and vertices in the figure. So for faces, each time you take away a cube, you aren't changing any of the existing faces, but you're adding 3 more. So you're like adding 24 here. And then from the vertices, when you like take away the cube, you like take away that one vertex that was originally there, but you're adding back 7 from you're adding back 6. You're adding back 6, I think. I'm sorry. You're not actually you're not actually like losing this vertex. It just goes pushed inside. You can think of it, and then there are just 6 vertices on the outside. Another way to think about it is like you're adding 8 vertices from the unit cube onto your figure, except for like one of them overlapped with an original vertex, and both of these like overlapping ones are no longer existent, so to speak. So you're losing 2 whenever and you're adding 8, so it ends up as +6 for each unit cube you're taking away. So on one side you have a +72, so that means the other side you also have a +72. And originally there are 12 edges, so 12 plus 72 is 84. So I guess this is like another approach that you could use for counting edges if you are more comfortable with counting the faces and vertices instead. So yeah, those are just 2 different ways to do the problem, and I guess a neat application of that formula. So yeah, next is this problem with lots of spheres, and I think this is the only one I actually started for this week. And the reason why I thought this problem was really important to know is simply because of how the diagram has to be accurate, and it might be a little bit hard to envision, and you have to take a lot of cross sections. So we'll get there. You have 6 spheres of radius 1 are positioned so the centers are the vertices of a regular hexagon with side length 2. So we can immediately start by drawing a hexagon, and we can let each of the vertices represent the center of a circle. Since we know that each side length is 2, that means the radius of each one is going to be 1. All right. So like I'm not like gonna draw all of them, but the circles are gonna look something like this. So they're all gonna like pass through the midpoint, and they're all radius 1. So these 6 spheres are all internally tangent to a larger sphere, which means that they're all inside of that sphere. So this is, you can think of it as like a 2D cross section or a plane cutting through the centers of everything. So you'd have the sphere that's going to be this large circle around this hexagon that's also tangent to every circle. So I drew it a little bit large, but I think you should get the idea of what the diagram should look like. So it's just like 6 circles and then 1 circle around all of them. All right. And then lastly, you have an sphere is going to be tangent to all 6 and still internally tangent. And what this means, it has to be kind of on top of the spheres. And so this is kind of hard to like draw in the diagram right now, So we'd have to use a different angle or a different cross-section to include that sphere into the diagram. So for now, we're only going to work with the large circle and the 6 smaller circles. So it asks what the radius of that last sphere was, and we'll get there. So the first thing you have to do is find the radius of the big circle, because other than the radius of the last sphere, it's the only thing we don't know in this diagram. So I'll just redraw this. So if we take our hexagon and just draw some circles that are all tangent to each other. And the sphere. So first thing to know is that the center of this hexagon is going to be the center of this large circle. And that is simply because the diagram is symmetric, so it has to be the center. And next, a regular hexagon has every angle is 120, so that like when you connect each vertex to the center, these diagonals are going to be collinear, and everything is an equilateral triangle. So this is a property of a regular hexagon, that everything is equilateral. So a regular hexagon is just 6 equilateral triangles put together. So knowing that, you can find that like the length from the center of the hexagon to a vertex is just 2, because that's the same as the side line. And then since I talked about this in the first week, the line between the center of 2 tangent circles will pass through the point of tangency. So this line, when you extend it past the center of the small circle, will intersect with the tangent point. And this has radius 1. So your total radius of the large circle is just equal to 3. So that would be how you would find the radius of the big circle. And now once you do that, you can draw a new diagram, but this time incorporating your last sphere in the diagram. So the only way to do that is to draw it vertically instead of horizontally, which is the first one. So if you do the vertical cross section, you'd have this big circle still. However, like your small circles will kind of look like this, and your center is here, and it goes all around, and then this last circle would be a tangent to this circle like that. And it would look, the diagram would look something like this. I am only drawing one of the smaller circles because drawing all like 6 would be redundant, since everything is rotationally symmetric. All right, so I do want to clean this up a little bit since there's so many lines for just a few circles. So it should look something like this. So for a few things to note, one, the radius, or this large circle that we don't know, it cannot pass through and cannot contain the center. And this is because if it did pass through the center, there would be really no way for it to be tangent to all the other spheres. So that's why I drew this above the plane of the hexagon here. All right, so now this is like a 2-dimensional problem, and you'd have to use the Pythagorean theorem to solve this problem. And the main idea here is you connect all the centers, and this is a right angle because this sphere is going to be tangent to all 6. So it has to be symmetric again, and the only way it's symmetric is it's directly above the center of the hexagon. So that'd be why this is 90 degrees. And after that, you just need to know the side lengths. So if I let the radius of the unknown circle be r, we know that this small circle is radius 1, and we know that this length right here is just equaling this length on the hexagon. So it's equal to 2. And lastly, this last height we don't know is just 3 minus r, because the total big radius is 3, and this section of the circle we don't know is r, as it's the radius. So we just have 3 minus r squared plus 2 squared equals to r plus 1 squared. And from here, you just have to solve the equation. And I guess I can do this since it's not that long. The r squares would just cancel out. So you're going to be left with like 8r equals to 12 and r equals to 3 over 2. So yeah, that would be the answer to this problem, 3/2. Are there any questions on this problem? So I guess my main point with this problem is simply just the importance of taking cross sections and using information from like various different cross sections from the diagram to like find what you need to like get the answer. So from the original problem, you'd find that there are like 2 things you don't know, which are the radius of like the 2 larger spheres. So you'd first find the one of the biggest sphere, and after that, that gives you enough information to solve the next one. So that's really it for this problem. Let's move on to this next one. And this one is really just one big cross-section problem. So it asks you to find a length of the portion xy contained in the cube with edge length 3. So it's pretty clear that xy is going to be this like diagonal from x to y, and it's going to pass completely through every single cube. So there's not going to be any part of this line that is not inside a cube. And I think you can just see it from the diagram mainly that like this diagonal is going to be completely contained within a cube. So I actually didn't draw this very well on the diagram. Well, I guess I did. It's just kind of hard to see this diagonal. But like the idea is that this is going to be a right triangle if we extract it from the figure. And we now have to work in a 2-dimensional problem to find some side lengths. So since this is going to be like the bottom diagonal of the cube, there's like a bottom leg is 4√2 for this big triangle, and this height is going to be 10. All right, and we don't know anything else. And we're asked to find the part with length 3. So the main idea here is that we have to split this height into sections of like 1, length 2, length 3, and length 4. And each section of this hypotenuse corresponding to that like height section, it's going to be how much of the length xy is inside each cube. So then from here, this is just a similar triangle problem. And yeah, I guess the cool way to do this is first you can find the total length hypotenuse. It's the square root of 10 squared plus 4√2 squared, or square root of 132, or 2√33. Yeah, and then we have to find just what part of this hypotenuse this is, right? So there are a couple of ways to do this. I guess the first way is just to find this total length from just this 1 through 3 part. So the total length of that is just 6/10 of the hypotenuse. Then we can subtract this 1 and 2 part, which is going to be 3/10. So we're going to be left with 3/10 of the hypotenuse and then times 2 root 3 over 2 root 33, and that just becomes 3 root 33 over 5. Alternatively, we can actually use the idea that each length of this hypotenuse is proportional to the height it sees. So the ratio of these lengths is going to be 4 to 3 to 2 to 1. And so then this is just going to be 3/10 of the entire thing, or 3 root 33 over 5. And that's really it. So all of this problem really asked you or tested you on was to find the cross section diagonally, and that'd be it. The square root 132 is from the Pythagorean theorem with this triangle that we formed. Since xy is going to be like two opposite corners, and these are all cubes, so everything's perpendicular. 132 is equal to 10 squared plus 4 root 2 squared. Since 10 squared is 100 and 4 root 2 squared is 32. So that's where we got the length. All right, so does that answer everyone's questions? Or? All right. So these are the last few problems. I do want to say the challenge problem again is on your bottom right, and if you do want to do that, you can. I won't be doing that. So, okay. So next we have when the centers of the faces, just for this problem right here. You have the centers are joined to form an octahedron. What's the volume of the octahedron? So the cool part about prisms is that like you can think of them as inverses of an octahedron. So an octahedron has 8 faces and 6 vertices. A prism has 6 faces and 8 vertices. So that's why you know that when you connect the center of all the faces, you're going to make an octahedron. And it's going to look like that. All right. And really the idea here is just you can find any of the bases, but let's just take the horizontal base since that's the way it's drawn. The horizontal base of this is going to be like a rhombus within, so it's the cross section through the middle. The sides are length 4 here and 5 here. And so the area of this shape is just going to be, since these are all midpoints as its center, it's just going to be half of the area of the entire shape. So the area of the entire rectangle is 20. The area of this base is 10. Then we know the height of the entire octahedron is just 3, which means that like the height of each pyramid is going to be 3 halves. So it doesn't actually matter here in this case. So your answer just be 2 times 3 times 10, which is the base. So base height, this is 2 for each pyramid, and times 1/3. So it's just 20. Okay. Yeah. So I guess we have 2 more problems left to do. So a sphere with center O has radius 6, a triangle with sides of length 15, 15, 24 is in space, so each of its sides is tangent to the sphere. What is the distance between O and the plane determined by the triangle? So this one is, I mean, it's 8, so I guess you can leave if you want. Or you, I mean, if I guess, how should I say this? You can leave, or if you want to stay while I do just this last problem, you can as well. So how about that? This is like mainly the same drill as past few weeks, and if you do want to watch, or if you do want to like, or you have to leave and you don't like want to miss anything, you can look at the recording on YouTube, That's going to be posted like in a few days on what you missed. So you are free to go, but I will still be going over this last problem. All right, well, goodbye. Yeah, for those of you who do want to stay, I'm only going to be doing this last problem. I won't be going on to this last page. So, because this problem is quite difficult to visualize as well. So we have a circle or a sphere, and its radius 6, and the triangle is going to be, it's going to look something like this, where you have like the triangle, it's kind of like a headband on the sphere, a triangular headband. And the main idea of this problem is that if we take the cross section in the plane of the triangle, this would just become 15, 15, and 24. And you'd have the incircle, like exactly the incircle of the sphere, of the triangle. And this is because we're given that each side is tangent to the sphere and that the cross section of a sphere is a circle. So that means it's going to be a circle that's tangent to every single side of the triangle, which means it has to be the incircle. Right? So from here, you can kind of figure out what this radius of the incircle is. And if we draw this like so, we know the radius of the incircle times the perimeter is equal to twice the area, or the in radius is equal to 2 times the area of the perimeter. And this was from the triangles thing that I talked about last like both weeks, last week and last week. So from here, the area is actually pretty easy to find because this is isosceles. We can just draw the height to just midpoints 12 and 12, and 5, 12. Then that means that this height is 9. And one way to see this is because this is just 3 times a 3, 4, 5 triangle. So 15 is 3 times 5, 12 is 3 times 4. This last height has to be 3 times 3. If you just don't see that, or you don't want to think about it, you can just do the Pythagorean Theorem. You'll get that this is going to be 9. So then the area is just going to be 9 times 24 divided by 2, or 9 times 12, or 108. So area here is 108. And the perimeter is just going to be 54, because 15 plus 15 plus 24 is equal to 54. And so the radius is 4. All right. So now that we know the radius, we can find the distance between O and the plane. So what does this mean? You can kind of think of this like how with a circle, it's like a circle and a chord kind of thing. So if we take a vertical cross section this time of this sphere, the triangle just becomes a line, and you would just like see the intersection of the plane and the sphere at this very vertical cross section is just a line, and the, I guess you can say, the property is that this chord is the diameter of the incircle. And the reason why this is true is because from our horizontal cross section, we saw that the intersection of like the circle and the sphere and the plane is just going to be the incircle. And so like that section of the sphere, like with the width, you could say that section is just going to be equal to the diameter of this like circle. So I guess that's the biggest observation. So from there, once you see that, we have the radius, the radius of this sphere is 6. And we also know that this diameter is going to be 8, since the radius is 4. So the radius is going to be 4. And notice that this is going to be a perpendicular going to be like perpendicular bisector of the chord because if we connect it to both endpoints, it's isosceles. So that's why I can just draw the height and say its length is 4. And lastly, we just need to know this length. So this is just from the Pythagorean theorem, 6 squared minus 4 squared, which is equal to the square root of 20 or 2 root 5. And that would be it. So are there any questions? Okay, well, if not, you guys can all leave. If you want to try like the remaining problems on your own, that's fine. Again, you can see solutions to everything just online as I've written the problems. So yeah, I'll see you all next week.